The future is here already. It's just not evenly distributed. Yet. Today's world teems with innovation. The nexus of hardware, software, and human ingenuity promises a revolution in possibilities. What does tomorrow look like? Witness Future Proof.
All right, ladies and gentlemen, hello and welcome back once again. Yours truly, Eric Cavanaugh is here. I am so excited to kick off one of the biggest events we've done in a while. Quite frankly, it's very exciting. The evolution of data science. That's exactly right. Presenters today, our very own Dr. Robin Bloor, Austin, Texas. Yours truly, Eric Cavanaugh. And we're going to dive right in, folks. Big thank you to our report sponsors, Anaconda, IBM, Iguazio, and Teradata. We'll hear from those last two today on the webinar. What is data science? So here's my definition that I made up all by myself. The assiduous management of information assets for the purpose of organizational optimization. Trying to keep it pithy here, folks. A lot of people think of data science as algorithms, basically, as R and Python and things of that nature. That's all part and parcel to the big picture for sure, but I would argue that data science is much more than prognostication. I would argue there are many other benefits of data science, and we'll talk about data science platforms today, what they are, how we got here. Dr. Bloor is going to explain kind of the process of what got us to this point today and what this all means. But there are tons of applications for data science. You can use data science in general for pattern recognition, pattern detection, but then you operationalize all that to take some action on things. And what we're really seeing here too is the scale out architecture of the future unfold before our very eyes. So there are lots of different things you can do with data science. For example, understanding employee behavior, employee analytics, who's doing good stuff, who's doing bad stuff. There are lots of different ways you can track that sort of thing. Self-driving data management refers to AI-enabled systems that can detect what kind of file you're uploading and determine what you're probably trying to do with it. So it'll give you recommendations in the interface that suggest where you're sending this document, what purpose this document serves. That stuff is really not all that hard to figure out if you get right down to brass tacks. And remember, machine learning algorithms don't sleep. They work all the time. So if you set it up properly, if you have a good platform, this is an architectural issue, if you have a good platform for data science, you're going to reap so many benefits downstream from that foundation. We hear a lot about deep learning. It's very exciting stuff, folks. There's no doubt. We're still not quite there. All the really smart people I talk to say that deep learning is still in its infancy. But the point is, deep learning can be used to solve for incredibly complex problems. It can be used for feature identification to understand. So think about how when you're working with an analytics platform, you're trying to understand things like covariance, which object or which track, which vector is indicative of something else. What can I pay attention to help me understand what's really happening? Let's take COVID-19, for example, this just dreadful little virus. How can we better understand what it's doing to the human body? But the point is, something like deep learning can really help us understand what the key features are. What are the facets? And a lot of times it's stuff that you're not looking at. I see morale going way up thanks to artificial intelligence, thanks to data science, for all kinds of reasons, because AI and ML typically allow you to tackle all sorts of really tedious, boring stuff that people didn't want to do anyway. So here's my bold prediction, folks. I believe that data science platforms are going to subsume data management in toto. In other words, traditional data warehousing, data movement, ETL, all that kind of stuff. I think in the future, in the not too distant future, data science platforms will be the epicenter, the foundation of application design, development, and delivery. And that's a pretty bold claim. And of course, we have Teradata on the call today. They've been the de facto leader in data warehousing for decades. And they saw the future as well. But I believe that data science platforms will form the foundation of the future business in the information economy. And I'm pretty sure about that. We don't have to climb the mountains manually anymore. Data science platforms are going to enable a whole new array of possibilities. If you scale out from the right foundation, from the right architecture, going into production is not a problem, and it's been a problem for a long time. This is some of the other data science leaders we wanted to tell you about. The asterisk shows the companies that talked to us and showed us what they're doing these days. Very cool stuff. Altair's been around, high performance computing, and now focused on the space. H2O started up as a library, now it's a very impressive platform. There's so much cool stuff happening in this space, folks. It's really taking off.
What we did was, over a period of about 3 or 4 months, we just took a look at what was happening in the area of data science and big data. Those two walk hand in hand. So in one way or another, technology in one space enables technology in the other space. So the question we're looking for is, what is a data science platform? That big data trend was really a data science trend, because data science was really 90% of what you could do with big data. So, and the reality in IT has always been that the applications lead, and the applications lead the technology. Nobody buys technology for its own sake except by accident. So businesses wanted to extract effective knowledge from their data. In the past 10 years at least, any other data they could get their hands on. So driving the trend, well, obviously the cloud, which allows for rapid deployment of pretty much everything that's to do with data science. The parallel processing that emerged with the open source software movement that began with Hadoop, but eventually involved an awful lot of components, some that were complementary to Hadoop, some which were, you know, in the Hadoop stack, and some which were in competition with what Hadoop was doing. But it all became an open source game. And because it was open source, it meant it was very easy for people to adopt the technology and prototype it. Then there was lots of big data stories that were coming out of places like Google, Facebook, LinkedIn. All of those companies had huge budgets with which they could play with data science in ways that no other companies could, you know. And also they're very good at employing the best people. Then we got the emergence of the data science program language. R. It began with R, but it moved to Python fairly quickly, because Python, in my opinion anyway, is a more capable language. But you suddenly got tools in the hands of, you could call them dilettantes in some ways, that could actually just, in one way or another, build their own algorithms in various ways. So statistics was enabled in a way that it had never been able before. Previously, people bought statistical software, but now you could actually write your own stuff, and a lot of people bright enough to do that. And then the machine learning libraries immediately started to rack up. And we had a whole stack of technology that you could actually use to build various data science applications. The technology cost was collapsing, basically. So it seemed like any old business could dip its toes in the water. But no, not really. Not so easy. This is what data science, it's how it used to be. Good old days. I mean, first of all, it wasn't general. And secondly, the people that actually did this were people that had graduated from universities with degrees that were either mathematics or math literate. And we had these various tools, SAS and SPSS were the main ones, that were the tools of choice. And they could do most of what actually is being done now, but they were expensive. This was a walled garden. The data scientists were on the inside and the IT was on the outside. And the data scientists could get data from corporate databases with ATL that the IT guys built for them to get their own little data stores and do data analytics on those stores and to build reports. So we moved to what we could call the data science project. And this is the story of the past 10 years, so to speak. Multiple data sources, possibly including data streams. You get data from anywhere and people were making it available. You might have to rent it or you might get it for free, but you could get it. Data acquisition. Well, we got Kafka from the open source community. All of a sudden, pipelining data became easy and inexpensive, and Kafka was actually a brilliant piece of software. But you've got data cleansing, which happens to be iterative. You needed a data store. And that, depending on what you wanted to do, might need to be an analytic database, could be a data lake, actually could be a set of flat files if you really wanted to do that. Data analysis itself is an iterative process, and integration of the results into production applications. There's this data cleansing thing. Even now, the statistics are suggesting that 80 to 90% of the effort that is actually involved in building a data science application goes into data wrangling and data cleansing. It's running the various algorithms that you need to run on top of data is not that difficult. And I've just listed here the various ways that data gets to be dirty. And that means that data science needs to deal with this, because data science is making predictions that are supposed to be dependable, accurate, repeatable, and so on. And you can't do that with dirty data. The story, the word from the herd is that at least 80% of early data science projects failed, and they did so for many reasons. And there's the big area of failure, which is scalability. Now that we're actually talking about the architecture of data science, there are actually, in my opinion anyway, 5 dimensions of scalability. One is very large data volumes, another is service level performance, and every project or data science platform will be limited at some time, at some point, as to what is possible because of these architectural dimensions. They're merciless when they kick in. Data science are a scarce resource. They always were. They're always going to be. People that truly understand the mathematics, it's you know, their numbers. There's probably about 500,000 of these people every year that graduate from American universities, and not all of them want to be data scientists. You know, executives who understand the data science business process and experienced data science teams, they're as rare as hen's teeth. So now we're talking about the difference between a data science application and the data science business process. And this is really what this presentation is all about. It's the distinction between a data science application and a data science business process. And there's a big difference. But even if you scale up, building an application is one application. You, in some way or other, looked at, I don't know, your hiring policy within an organization. You built one app, it works fine. But that doesn't mean that you built a business process. Here's what I would describe as a data science business process. We've broken it down really. We've got a development environment that involves data gathering, data cleansing, data ingest, analytical prototyping, production interface. All of those things are, if you like, development activities. And then you've got a production activity that involves all of that stuff, but also involves data governance, and it also involves DevOps. And we're now looking not at an application, we're looking at a whole process. In other words, all the data science that's going on in the organization in one way or another is going to run through this bottom layer. If data governance was important before big data, and it was, it's far more important in the era of data lakes and big data science. With data governance, you need to know what the system of record is, and the system of record has got to be a record of what the company actually did with data that's real. There needs to be data provenance and lineage for all the data wherever it came from. You need to have rules for data cleansing in terms of what you will allow within the environment that may not be entirely clean data. You need to have data security pinned down right from soup to nuts in terms of the whole of the processes that you're running. You need compliance to whatever regulatory things exist, from GDPR in the big way to anything that is in your sector that involves regulation of the use of data. You need to be able to know that you have data integrity. You need an audit record of everything that happened. You need data lifecycle management, and you need to know the meaning of data, which means that you need to have a proper metadata management thing spreading across the whole of the system of record. Nobody that I'm aware of has this. They have, some of them have, some organizations have a lot of this, but nobody that I'm aware of actually has all of this. Everyone's moving towards this. But the point here is that data governance is a perpetual process. What you're doing with data science is you develop models, you train the models, you deploy the models. And the people that are interested in this are a whole series of people, data scientists, business analysts, or what they now call citizen data scientists, data engineers, developers, the DevOps people. All of these people are actually in some way or other plugged into the platform. And you've got a cycling activity of review, design, build, validate, deploy, and that just keeps turning on. And this is the full automation of a business process I'm depicting here. Now, the last thing to state is is that I just want to draw a line between event-based AI and the AI, the data science as we know it now, because what's occurring, moving to an event-driven world, and with that you require an architecture that's real time. So what I'm suggesting is that the architecture for data science is bifurcating between those applications that really need to be a real-time stream that's that's injecting itself into production applications on a fraction of a second basis, and other stuff that's more big picture stuff that will never be real time. There's two parts to it, but I just thought I'd make some comments about the event-based part. First of all, here's what the events are. There are a lot of things that you can describe as events, but when something new happens, instantiation, a state report of anything that's going on out there, from an individual's data through to any device and so on. Trigger events when thresholds are passed, correction events when data is changed. And you also need to consider data refinement, aggregations, homogeneous collections, and derived data. In other words, it's a complicated thing. But what you're actually attempting to do is there's a kind of event window that streams processing looks at, possibly looks at historical data, and in one way or another applies algorithms to take decisions in real time. So you can think of events as drops of water. They can live in streams, and also live in data pools and data lakes and database engines. If we were changed to a real-time event-based world, we would have to change how we write applications. Real-time AR is architecturally different to non-real-time AR. It's just a point I'm making. Data science, it ain't like it was. Platforms are what it is. It's only just begun. In other words, the things that we're talking about and the vendors who are being responsive to this are on the edge. But, it's all in development. It's only just begun. And we're moving toward real-time AI. It's going to become part of the picture.
We have Iguazio on the line, dialing in all the way from across the planet. Yaron Habib, I believe you are out there. Can you hear us?
Great. Just a few words on Iguazio. Iguazio is building a data science platform used by major companies. And it essentially has 3 layers. The first layer, the lower layer, is data. We do have a pretty high performance data engine. Think of it like distributed memory, just a device running on flash and SSD, so very, very fast, but very cost effective. Our data layer is essentially can impersonate as many different things: a file, object, column, a row, key value, time series, etc. And again, all of those can be handled in pretty high performance. On top of it, what we provide is a managed set of services, both serve the equivalent services of Hadoop, Spark, Presto, Hive, all those. In addition to all the new services, the more modern services for data science, deep learning, machine learning, and a set of serverless functions, which are also high performance and stateful, so they can process data. There are 2 kinds of serverless functions, ones that are more interactive, like Amazon Lambda, just about 100 times faster, and ones that are more jobs, so you can do data analytics jobs or machine learning jobs like training, and you could also build pipelines that comprise of multiple steps and multiple functions. That's sort of the middle layer. On top of it, you have a further abstraction layer that allows you to do more complicated and sophisticated things like AutoML, exchange different kinds of experiments with different algorithms and different parameters for the algorithms and choose the best. Do experiment, job, and data tracking in an automated way without writing a lot of code. Feature store for both online and real-time and sort of offline data. And a workflow management based on a platform called Kubeflow, an open source project called Kubeflow, that allows you to build end-to-end workflows and full automation and CI/CD for your data science.
You really thought through the end-to-end process, not just of gathering data, applying cleansing rules, building models, but also deploying those models at scale. And that there's a lot to be said for Nucleo, as part of this process, but also just serverless in general, right? Can you kind of expound on that for a minute?
Yeah, so we've seen that most of the energy initially in data science is around the research and experimentation phase. But where most people struggle is in the move to production and operations. So someone wants to build a pipeline, let's say for a real-time recommendation engine, that requires taking the code, containerizing it, making it run 24/7, logging, monitoring, security, handling larger scales than what you usually do on experiments with a CSV and an Excel spreadsheet. So that requires for some automation. The best automation for building code into something that runs in production is serverless concept. The problem with serverless concept that usually they're slow, they're stateless, etc. So you have a combination on our solution for serverless engines that are extremely high performance. They're so high performance that if you take your own Python code and run it within the serverless engine, it will run sometimes a magnitude faster because of all sorts of real-time tricks. And they're stateful. There is this real-time data fabric that allows you to build pipelines that essentially one step in the pipeline will gather data, whether it's from ETL or streaming or whatever. Second step in the pipeline will run denormalization and create features and do analysis on the data to form the data set used for training. Another step in the pipeline could be the training, and then another step would automate the build of the serving functions and the APIs and the real-time features required for that serving function. So the general idea is that with few lines of code, you can build things that could take months without this, because most of those things are automated. Another effect of making it serverless is that everything that you run runs within sort of a sandbox that records everything. So you automatically get artifact management, job tracking, all of that within the same platform.
For those who don't know, Anaconda is an open source project. Of course, they do have an enterprise edition. They really wanted to build out a platform to allow data scientists to use Python to do all sorts of interesting things. So they're a very forward-looking organization as regards the use of Python and data science in general. And Imad Baroudi is out there from Teradata. Imad, if you will, take it away. Tell us a bit about what we're looking at here. And I'm just fascinated by Vantage and by what Teradata has done with Presto as well. But tell us what we see in the slide here.
Thanks, Eric. Yeah, absolutely. This actually goes back to what you were saying about data science platforms will be subsumed, will subsume data management, and I couldn't agree more. In fact, that's really what we've done here. And not only do I agree that they're going to merge, I think they have to, in order to get that line between initial discovery and early data science work to get to operationalization and productizing your work. I think they have to merge. Everyone knows Teradata database, and to the point you made earlier, several years ago, we bought a company called Astrodata, and we merged those together. And that's the result of that is Teradata Vantage, which is the merger of both of these. And we show it in this way in that the parts in blue are where Teradata Vantage sits, and we show it within the larger ecosystem. If you going from left to right, the whole process that that Robin outlined, from sourcing data and cleansing it, ingesting it, and managing the data, all the way out to writing your analytics and productizing it to the end user. This is what you're seeing here on the slide, which is the larger ecosystem, and the blue part is where Vantage sits. And there we have a relational engine that not only stores data, but we can store non-relational data as well and process that data. With the analytic engines, have a SQL engine running advanced SQL capabilities with math statistics, machine learning scoring, and then you also have machine learning and graph capabilities for more of the advanced analytics capabilities. The key here is that all of this runs and acts as one system, and this is the key to success: having one technology that's working together, so that your data scientists, the business analysts, all the way up to reports, the basic Monday morning reports that go to the CEO, are all running on the same platform using the same data, just different slices, different views, and different tools against them. And knowing that different users have different skills, different capabilities. And Robin was referring to this in the where he was talking about the trends, that the big data trend really was the data science trend, only in the early days. And as he outlined that, I was thinking of all the key points he made about running in the cloud and parallel processing and languages and tools and libraries, recognizing the different users want different languages and different tools. We're catering to that. In fact, you look at the top languages that are used in the analytics world, in business analytics. There's SQL, R, and Python. Those three are the top, and anything else is kind of a distant second, really. And so we've made it to where whether you're submitting analytics, writing analytics, processing them, whether you're doing them in SQL, R, and Python, we don't care. Those come into the engine, they get processed. In fact, R and Python, which are natively non-parallel languages, right? They run in one memory space. We take those and we make them parallel. So you can code on your desktop without any regard to parallel processing or distributed data. We take that and we scale it and run with it, and then providing all the tools to users. And a couple key things here. This is a software platform. Where it's deployed is up to the user, up to the organization. So we have the exact same software, bit for bit identical, that runs on premises, on VMware, on our hardware, on VMware, or on the cloud, AWS, Azure, Google. It's the same exact code base. So it makes for application portability easy. It makes for hybrid cloud deployments very easy, transparent.
IBM here, and of course IBM bought Red Hat, which has been the enterprise open source service provider for a long time now. They are the de facto leader in that regard. But what I've heard is that their cloud is going to be fully open source. Their prescriptive approach to the AI journey, and I like this, and you really saw Robin talk about this as well, Dr. Bloor. You infuse operational AI throughout the business, you analyze it. That's called instrumentation, really, but not just instrumentation, operationalization, if you will, of AI, and analyze, organize, collect.
And the thing that's kind of the theme of what we're talking about here, and certainly all of the sponsors, has been to talk about making this a business process. You have to collect the data. In other words, there's a whole data layer right underneath. You have to organize that in order to create an analytics foundation. The analyze phase is a very sophisticated phase beyond, throwing some mathematics at some data. And then you actually have to operationalize all of this stuff. So this is an end-to-end activity to implement AI. And IBM's represented it as a ladder, and that's a fair representation, I would say. And then I've got this word modernize, and yeah, that's true too. And that's part of the issue, if you like. You're going to have to, in one way or another, be able to make all of your data stores and data flows. They're going to have to function a kind of flexibility that they'd never necessarily had to do before. And you actually have to be able to deploy it anywhere.
Thank you so much to our sponsors, to Imad and of course Yaron and the team at Iguazio and Teradata. And thanks again, folks, so much for your attention. We'll talk to you next time. Take care. Bye-bye. Hop online to insightanalysis.com for more information. That's where we'll post the archive. And folks, we want to know what you want to know. So if you have any thoughts about all this, send me an email, info@insightanalysis.com. That comes straight to me. And like I say, we're keen to understand what your impressions are. We want to know what you want to know. Send me an email, info@insightanalysis.com. With that, we're going to bid you farewell, folks. We'll talk to you next time. Take care. Bye-bye.